Chapter 15 Optimization of Multiple Logistic Regression Model. We have learned about the optimization of logistic regression models. In the examples above, for simplicity, we have mainly used a simple example of a logistic regression model which contains only one predictor variable. In practice, however, logistic regression analysis is often performed with two or more predictors. In this chapter, we will explain the computational methods in the optimization of a logistic regression model with many predictors. To understand the logistic regression optimization, it is important to understand the basic mathematical concepts of vectors and matrices. These concepts help describe the data structure and computational methodology of a logistic regression model. A vector is a sequence of numbers or variables that has direction and magnitude. In machine learning, vectors are typically used to represent features of data points. For example, if a person's age, height, and weight are features, they can be represented as this single vector. A matrix is a two-dimensional array of numbers or variables. In machine learning, matrices are used to represent the features of many data points together. Each row represents one data point, for example, a single person. Each column represents one feature. The dot product of vectors is computed by multiplying the corresponding elements of two vectors and adding all the results together. Here is an example of inner product calculation using two simple vectors. Vector A and vector B are defined as follows. The formula for the inner product of vectors is to multiply the corresponding elements of the two vectors and sum the results. Substituting the numerical value of each vector into the formula, we find that the inner product is 23. In logistic regression, the dot product of the predictor vector and the parameter vector means multiplying each predictors by the parameter and adding them all together. This reflects the magnitude of the impact of each predictor on the prediction result. When a logistic regression model contains many parameters, matrix calculations are used in the optimization process. The reason for using matrix calculation is to efficiently compute and update partial derivatives. In a logistic regression model, for a given predictor vector x, the probability of occurrence of y is modeled in this way, where xi is the predictor variable and beta I is a parameter of the model. In matrix form, using the inner product of the vector of predictor x and the vector of parameters b, the model can be expressed in this way. Here, X is an m by n matrix of predictors. M is the number of observations and n is the number of predictors. Beta is an n by 1 vector of parameters. X beta is an m by n vector, representing a linear combination for each observation. During the optimization process, the gradient of the loss function is calculated, and parameters are updated based on this gradient. The gradient is often represented by a matrix, as in this equation. Here, xt is the transpose matrix of X. Y is the vector of the Lavel's observed values, that is, the actual values of the dependent variable. y hat is the vector of predicted values. Using this gradient, the parameter vector beta is updated by this equation, where alpha is the learning rate. In this way, matrix computation plays a central role in the optimization of a multiple logistic regression model. It allows for efficient handling of models with large amounts of data and numerous features. Let's look at a simple example. Suppose there are three predictors, x1, x2, and x3, and three observations or data points. To include a parameter, beta 0, which is a constant term, we create a matrix by adding 1 to the vector of each data point. This is the matrix of predictors. The vector of parameters, beta, will look like this. The logistic regression model takes the inner product of the vector of predictors and the vector of parameters beta, and applies the result to the sigma function to apply the predicted probabilities. By applying this process to all data points, predictions can be computed efficiently. In the following, we will use an example to illustrate the process of calculating the gradient of the loss function and updating the parameters based on this gradient. Suppose the actual label y and the predicted label y hat are represented by these vectors. The y hat represents the probability that each data point is positive. First, the prediction error is calculated by subtracting the predicted label from the actual label. Then, computing the product of this prediction error and the transpose matrix of the matrix X of the predictor variables, we obtain the gradient of the loss function. This gradient represents how the loss function varies for each parameter. Specifically, we update the parameters by subtracting this gradient multiplied by the learning rate from the parameters. This update step is repeated to minimize the loss function and optimize the model.